It's spring, so in exercise 8.4 we find ourselves in the garden of two neighboring homeowners. And different from the previous exercises, we still do game theory, but now the actions are not in terms of a very limited number of actions of 2 or 3, which can be represented in terms of a matrix, but each player has a continuous range of actions. And in this case, the action that can be taken is how many hours to spend on maintaining a beautiful lawn. And the number of hours can be anything between 0 and 24 hours a day. But that's not what they will do, because there's also a cost of gardening. But in the exercise, the average benefit is given by 10 minus Li plus Lj divided by 2. And that's the average, so not the marginal benefit, but the average benefit per hour of gardening. So the total benefit is the average benefit times the number of hours one of the neighbors spent. So you multiply this one, if you consider neighbor 1, you multiply this number by L1. And you can also see that the average benefit per hour for a neighbor is negatively dependent on the own effort. So the more you do in the garden, okay, the first hour the benefits are higher, but the more hours you spend, the average benefit over all the hours that you spend is decreasing. But importantly, it's also increasing in the number of hours that the neighbor spends, because you can spend time in your own garden, but the benefits are much higher if your neighbor also has a nicely maintained garden. Otherwise, you don't enjoy it as much. The opportunity cost per hour is constant and set at 4. And as said, homeowner I's average benefit is increasing in the hours that the neighbor spends on his own lawn, because the appearance of one property depends in part on the beauty of the surrounding neighborhood. And if you need to do the cleaning in your student home, you may have the same, that the average benefit of your cleaning effort positively depend on what your fellow roommates do in terms of cleaning. Okay, in question A we need to compute the Nash equilibrium, then in B graph the best response functions, and then also, let's see how the graph will change if the intercept of one of the neighbors' average benefit functions falls. But we will get to that. Start with question A. Compute the Nash equilibrium. Number of steps here. So first, we need to know what we want to maximize. And if we have neighbor 1, what this neighbor wants to optimize is the total benefits, which are the marginal or the average benefits times the number of hours spent, minus the total cost. And the total cost is, each hour spent comes at a cost of 4, and the total of hours spent is equal to L1, so the total cost is 4 times L1. And the neighbor takes the effort by the other neighbor as given in choosing his own optimal effort level. So choosing the own optimal effort level L1 amounts to taking the first order condition of this objective function with respect to L1. So we take the derivative of this thing and we get 10 minus 2 times L1, because here we have minus L1 times L1 is minus L1 squared. Taking the derivative of that is minus 2L1, plus L2 divided by 1/2. Neighbor 1 takes this one as given, so it takes L2 as being a constant, minus 4, because the derivative of minus 4L1 is minus 4. And then we can simplify this a little bit, and we get the following expression. And now we can use this expression to back out the best response function of neighbor 1 contingent on the effort made by neighbor 2. So solving this one for L1, we get that the optimal effort, the best response to the effort level L2 put in by the neighbor is for neighbor 1 to spend 3 hours plus the number of hours that the neighbor spends divided by 4. And likewise, for neighbor 2, we have a similar best response function, because this is a very symmetric game. So the best response function for neighbor 2 as a function of the effort paid by neighbor 1 looks very similar, but with the indices 1 and 2 interchanged. So we have two best response functions, and we can now solve. So in the best response function of neighbor 1, we can replace the L2 by the expression for L2 that we have over here. So we replace the L2 by the green term. So here we have it, and then we simplify. So 3 plus 3/4 is 15 over 4. L1 divided by 4 divided by 4 is equal to 16. So actually it's better to correct this on the fly. So this is L1 divided by 16, and we can now bring this L1 term to the left hand side. L1 minus 1/16 of L1 is 15 over 16. L1 should be identical to 15 over 4, and solving this we get that L1 is equal to 4 in the Nash equilibrium. Same holds for neighbor 2. You can easily see that by plugging in the number 4 over here for L1. 3 plus 4 divided by 4 is identical to 4. So given that the other neighbor puts in 4 hours of effort, it's optimal for you to spend 4 hours as well. So both neighbors spent 4 hours in the garden. Now we can graph the best response functions, and we are asked to do so in question B. And that leads to the following graph. So the thing to choose is the effort level L1 and L2. So we see them on the X and the Y axis. And then, for example, for neighbor 2, the best response function has the following form. If neighbor 1 puts in 0 numbers of effort, this one is equal to 0, and it will be optimal for neighbor 2 to put in 3 hours of effort. Then if for every hour that neighbor 1 spends in the garden, it will be optimal for neighbor 2 to increase the effort level by 1/4 of an hour. So the slope of the best response function is equal to 0.25. And yeah, it moves upward. So this denotes that the effort level in this exercise, they are strategic complements. The marginal utility of spending time in the garden increases with the number of hours that the other neighbor spends in the garden. And the best response function of neighbor 1 looks similar. Also, if neighbor 2 spends 0 hours, neighbor 1 will find it optimal to spend 3 hours in the garden. And also his optimal level of effort is increasing in the effort level of neighbor 2. And then we get one point of intersection of the best response functions, and this is our Nash equilibrium, where both neighbors spend 4 hours in the garden. That completes question B. Then we have, and in this case, owner 1 at the equilibrium point receives a payoff of 16 by plugging in the numbers, the equilibrium outcome of 4 hours each, into the objective function. Then in question C, we need to show how the equilibrium would change if the intercept of one of the neighbor's average benefit functions fell from 6 to some smaller number, which means that for one of the neighbors the benefit gets smaller. So suppose for neighbor 1, meaning that, okay, for any effort that neighbor 2 spends in, it now becomes less attractive for me to spend the original amount of hours. So the best response function of neighbor 1 will now move to the left.